with Oscar class. That's my dad.
Alright, now we're going to be looking at solving inequalities using multiplication and division. Now this works very much similar to other one-step equations that we're used to solving, but inequalities add one additional caveat to it, one extra catch, one extra warning to watch out for. So let's start with a fairly straightforward example. 3x is greater than equal to 27. So what we're looking for here are all the values of x that would make this overall statement true. So if I have a number line, where on this number line can I identify values I can plug in here that would make a true statement? So for example, if I'm just going to guess and check some numbers, I might think about the number, we'll put maybe a 10 in here. 10 times 3 is 30, which is indeed greater than 27, so 10 would be a solution. I could put in the number 2. 3 times 2 is 6. 6 is not greater than 27. 2 would not be a solution. So if I'm guessing and checking my way along here, I know that 10 is a solution, 2 is not. Now, obviously we want something better than that, than just guess and check around, so we'll do some classic algebra we're used to, which would be to divide each side by 3, and now have this statement. X is greater than or less than 9. Now that jives with what we expect, because again, we know 10 is a solution, 2 is not, so if I mark off 9 on my number line, I know 9 represents a potential solution. It's equal to, so we put a solid circle on the 9. We want numbers that are greater than 9. So greater than is off to that direction, but going off onto our right. So we'll go ahead and we'll create a shaded arrow pointing to the right. So we now have our solution algebraically, and we have the graph of our solution, which should fit fairly consistently with what we would expect. Let's look at a couple more examples, because this hasn't gone to the one dangerous thing that can happen when you multiply or divide both sides of an inequality. Now, when we're dealing with inequalities and we're multiplying or dividing each side by a number, there is one thing we want to watch out for. So let me start with a concrete example to illustrate why this is the case. I do expect this to be written down. Let's take an inequality we already know the truth of. 5 is greater than 3. Now we can agree on that. 5 is a larger value than 3. It's more to the right on the number line. So what happens if I take this inequality and I multiply both sides by -1? So I'll multiply by -1, multiply by -1. Let's see what happens. Now I have -5 and -3 on each side of the inequality. Now, if I carry the inequality sign down, I would write it this way. When I look at that, I know that's no longer a true statement. -5 is not greater than -3. It's more to the left of it on the number line, making it a less than value. If you think about your number line, there's 0, there's 3, there's 5, -3, and -5. Now, our original statement, 5 is greater than 3, makes sense. 5 is more to the positive side on the number line. It's a larger value. However, here, this is not true. -5 is not greater than -3. -5 is more to the left on the number line. So in order for this statement to be true, I have to change the direction of the inequality symbol. This is the case whenever you multiply or divide by a negative number. You have to switch the inequality sign. When we work our problems and we include this step in our writing, this is one of those important steps to write down every time we do it, because what it does is it reinforces in our minds that this is a rule we have to apply. This gets into part of why I expect you to write your steps next to your work and all problems to help reinforce why these rules are there and what the rules are themselves. Let's take a look at an actual example problem that puts this into practice. Alright, now we're going to use this rule involving the negatives to actually solve a problem. So we'll start with one that has a negative in it. Let's take 2x, negative 2x, is strictly greater than 16. Now, let's think about some numbers that are going to make this true and do some guess and check in order to verify the rule before we even get rolling too far down the line. So if I have my number line, here's my number line. Let's guess some numbers and see which ones happen to work. What if I put in the number 5? So there's 5 on my number line. 5 times negative 2 is negative 10. That is not greater than 16, so that's out. Let's try negative 1. Here's negative 1. Let's see, negative 1 times negative 2 would give me positive 2, which is still not greater than 16, so that's out. How about negative 10? So negative 10 might be down here. Negative 10 times negative 2 is going to give me a positive 20. Positive 20 is greater than 16. All right, that bodes well. How about negative 11? Negative 11 is right there. Oh, be on the other side of it. Negative 11. There's a negative 11 right there. That's going to give me a positive 22. Negative 2 times negative 11. Positive 22. Greater than 16. Okay, we're getting some numbers here. How about negative 9? It seems like this is a good region. Let's try positive 9. Positive 9, negative 18, not greater than 16. So that positive 9, that's out. But negative 9 checks out. So I'm starting to see it's all going to be down in this region, this very negative area. Now, let's solve it algebraically and see what we get. I'm going to divide both sides by negative 2. Now I note that I divided by negative 2, which means I flip the inequality. So that means x is now less than negative 8. That jives with what we are seeing in our guess and check area. These positive values are not checking out, and the negatives are. So here's negative 8, right down here. And now it's strictly less than. So I make an open circle on the 8, and I shoot off to my left. And there will be my graph. So here's the solution algebraically, and this would be the graph of my solution. Remember, when you use a negative number, I have to flip the inequality sign around. Otherwise, it doesn't work. Now these rules also apply to multiplying. Let's look at one of those as our last example together tonight. We're going to do one more, but this one's going to involve a division built into the problem. So let's say we're looking at this as our problem now. Negative x over 3 is strictly greater than, no, let's do strictly less than. Strictly less than 4. We're going to skip the guess and check portion. Let's just get right into the algebra. I have divided by, so I'm going to multiply both sides by 3. Now there's that negative hanging out there as well, so maybe we should do that first. We want to work our way in. I'm going to multiply both sides, divide both sides by a negative 1. Divide both by negative 1. That gets rid of that negative, leaving me x over 3 is less than 4, negative 4. But remember, I divided by a negative, so I flip the sign. I divide by a negative, flip the sign. Now I can go ahead and finish my problem. I multiply each side by 3, multiply both by 3, and I now have x is greater than negative 12. That would be the algebraic solution. And now I can go ahead, oh, that's a terrible number line. Make a number line. Let's see, here's negative 12, there's 0, I want greater than it. It's not equal to. I make an open circle on the 12, and then I'm going to shade off to the right. There's a big old arrow pointing that way. happy little arrow. There you go. All right. Hopefully when you come in, we'll be able to start looking at some more of these examples and dive right in on the U-tries. It is very similar to where we started off with our one-step algebra problems. One thing to think about is that when we divide by a negative, we have to flip the inequality sign around in order to keep it true. All right, have a good one.